All right. All right, so we're going to start talking about limits today. Limits, like I said, like I was mentioning before, limits are really, that's the main idea, the thing that makes calculus possible, essentially. And the idea of a limit is we want to talk about what happens when things are close to each other in math. So the limit has to do with how we define closeness. So the way we're going to describe a limit, you'll end up making it more technical in your calculus class. But what we say for a limit is if some function, it gets arbitrarily close. And by arbitrarily close, we could also say as close as we want. And that's the part that you'll make more rigorous in calculus. What do you mean by arbitrarily close? Gets arbitrarily close to a single number. We could say unique. Single number L as x gets closer to c. So as x is, we keep changing our x value, and as x gets close to some number, our function is getting closer and closer and closer to some single number L. We call L the limit. L is the limit of f of x as x approaches c. And we write the limit as x approaches c of f of x equals L. So as x gets closer and closer to some number, our function is getting closer and closer and closer to some value. Remember another time this year when we talked about functions getting closer and closer and closer to something? Asymptotes. So we're going to make a relationship between limits and asymptotes as well, which is kind of nice because we use some of the same rules for limits as we do for asymptotes. So this is our idea of a limit. And the part that you'll make more technical later is what we mean by arbitrarily close. You can say as close as we want, something like that. Now as we move forward, it's important. What the important thing to remember, and it's easy to confuse when we're talking about limits, is it doesn't matter what the function value is. All that matters is what it's getting close to. That's all we're worried about. Not what it equals. What is it getting close to? So we're going to look at limits three different ways. We're going to look at limits in tables of values. We're going to look at limits with graphs. And we're also going to look at limits algebraically. Today we're going to work mostly with graphs and with tables, and we'll come up with our first easy rules for working with limits. So let's look at a couple of examples. So let's say the limit, we want the limit as x approaches 4 of x minus 1. And we'll show how to do this in your calculator in just a second. But for this one, they give us a table. So this top row is x, and the bottom row is f of x. And when x is 3.9, so we were getting closer and closer to 4. X is getting closer and closer to 4. F of x is 2.9. When x is 3.99, we're getting closer. X is 2.99. And we want to know what our limit is, what our function is getting close to when x is getting close to 4. I'm going to go over on this other side here, 4.001. And this function is 3.001. And finally 4.1 and 3.1. So what, as x gets close to 4, here and here, what is our function getting close to? 3. So we say the limit as x approaches 4 of x minus 1 equals 3. Now in this particular example, when we plug in x equals 4, we get 3. Doesn't always work that way. What we're interested in is what is f getting close to? What is our function getting close to? It's getting close to 3. All right, questions on that one? That one's a pretty easy example. All right, let's look at one that's a little trickier. Not trickier to figure out, just our function's a little trickier. All right, so we have the limit as x approaches 2 of x squared minus 4 over x minus 2. And we'll put up a table, and I'll show how we come up with a table in our calculator for this one as well. What happens when we plug in, if we were just to try to plug in x equals 2 into this function? Our denominator turns out to be 0. It's a domain restriction, right? And if we remember back to when we worked with rational functions, and we were talking about asymptotes and all that kind of thing, what would we do to try to simplify this rational function? You remember? What would we do with this numerator? Factor, right? So this factors to x plus 2, x minus 2 over x minus 2. So we have a factor of x minus 2 in the numerator and denominator. What does that tell us happens with the graph of the function when x equals 2? There's a hole in our graph. So the function doesn't exist when x equals 2. There's a hole in the graph. Doesn't exist. But we can still talk about the limit. So here's my table for this one. I'm going to say that's fx and that's f of x. And here when x is 1.9, f is 3.9. 1.99 here, we get 3.99. We want to know what happens when we're getting close to 2. I'm going to go on the other side. So what is our function getting close to as x gets close to 2? 4. So the limit as x approaches 2 of x squared minus 4 over x minus 2 equals 4. Because our function value is getting close to 4. But we can't just plug in x equals 2 because it's undefined. And if we had a graph, the graph of this function we'd end up with something like this. And as we got close to x equals 2, on either side our function value, this y value, would be close to 4, even though the function doesn't exist there. So let me show you how to, or remind you, we've done a few of these, let me remind you how to make these tables in your calculator. So can I close my calculator? So it's going to take a second to get this started up. So again, just the one of the points of that last one, the function value and the limit are independent of each other. All right, so I'm going to go to my y equals, and I'm just going to graph that function. I'm going to put that in my y equals. So I have x squared minus 4 divided by x minus 2. So if I graph that, there's what my graph looks like. And at x equals 2, we can see that our calculator is not showing us the hole in the graph, but we can see that our graph isn't doing anything crazy. To see our table, you just go here to your table. I'm going to do second table. Oh, and if your calculators are still set from your Conics project, go up here to Format, and you want to turn your axes back on. So they're probably set to axes off. So we did second Format here, and you want to go to axes on to turn those back on. So that's here in the Format. All right, so then I go to my table, and there's my table. And this one, my x's are changing just by 1. So let me show you how to change that in your table. So our calculator says that x equals 2, we get an error, but the function value is getting close to somewhere between 3 and 5. So I'm going to go to here to table set. So the second window. And I'm going to start my table at, I'm going to say 1.8, because we want to be close to 2. And this delta table, that's how much we change each time. I'm going to set that to 0.0, I'll do 0.1, just do it by tenths here. So I just change this to 0.1 from 1, and I'm going to go to my table. And now as I get closer and closer to 2, I go 3.8, 3.9, and then 4.1, 4.2, and I see that I'm getting closer and closer to 4. So that's how I generate the table in the calculator. And I could change that table set. I could change this to 0.01. And then I'd change this. I'm going to set that to, that's probably okay. So I go to my table. And here we're going up much more slowly. And we see that we're getting closer and closer and closer. My y value is getting closer and closer and closer to 4. But at x equals 2, I get an error. And then on the other side, I'm really close to 4 again. So that tells me my limit is 4, even though the function doesn't exist when x equals 2. Just that function, x squared minus 4 over x minus 2, the one we used in the example. All right, questions on the calculator there? Okay. So let's go back, let's do another example. This time we'll just look at the graph. So you'll have some homework problems that'll say look at the table, and you'll have some problems that say look at the graph. So you want to use the graph to find the limit as x approaches 2 of x minus 2 over the square root of x plus 2 minus 2. So if we just try to plug in x equals 2 here, what happens? What do I get in the numerator? 0, right? In the denominator I get 0. So I get 0 over 0. That doesn't tell us anything. So let's graph this thing. So we want to use the graph to find this limit. So I'm going to go to my calculator. I'm going to enter that function in the y equals. So I have x minus 2 divided by square root x plus 2 minus 2. And I'm going to graph that. So there's the graph of that function. And then I'm going to go to my trace. And I'm going to go to where x is about 2. So I'm just going up. Here we're at 1. 1.5. What does it look like the function value is getting close to? 4. So on either side of 2, I'm at 3.99 here, at 4.02. So that from the graph is telling us that the limit for that function is 4. Even though the function at that point, at x equals 2, does not exist. The function value is independent of the limit. All right, questions so far? All right. So sometimes limits fail to exist. The limit does not exist. So we have several cases where limits fail to exist. The first one is when f approaches different values from the right and left. And an example of that would be if we were looking at the limit as x approaches 1 of the absolute value of x minus 1 over x minus 1. If I looked at the graph of this function looks like this. And this is y equals 1, and this is y equals negative 1, and here's x equals 1 there. So from the right, my function value is 1, 1, 1, 1, 1, 1, 1, 1, 1, staying close to 1. But from the left, my function value is negative 1, negative 1, negative 1, negative 1, negative 1. It's different as we come from different directions. So this limit would not exist. The limit as x approaches 1 of this function does not exist. Because the function values are different from the right and left. The second case, when the function value, or when the limit doesn't exist. F of x is unbounded. And the other way we can say that is becomes arbitrarily large or small. So can we think of an example we've talked about in the past where our function gets really, really large or really, really small? Gets really, really large and really, really small. Exponential functions, as x approaches infinity, are the limit, and we'll talk about limits as x approaches infinity kind of as a separate thing, but that's one example. Can we think of another one? How about vertical asymptotes? When we have a vertical asymptote, our function goes way, way, way up, or way, 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 way down. So that's what we mean by arbitrarily large or small. So an example would be the limit as x approaches 0 of 1 over x. If we graph that thing, the graph looks like this. And it has a vertical asymptote at x equals 0. So as x approaches 0, this function from the right-hand side goes to positive infinity. From the left-hand side, it goes to negative infinity. Another example would be the limit as x approaches 0 of 1 over x squared. And that one looks like this. So as x approaches 0, our function is approaching infinity. It's unbounded. So that limit does not exist. And then finally, when f of x oscillates. So it's not approaching one single number. And an example of that would be the limit as x approaches 0 of the cosine of 1 over x. And that function, if we graphed it, it's kind of an interesting one, looks kind of like this. Goes like so, and then as it gets close to 0, it just goes up and down really fast. And it looks kind of like that. As x approaches 0, it's not approaching one single number, because we can move over just a tiny bit, and it's approaching some other number. Positive 1, negative 1, positive 1/2, negative 1/2, 0. So it doesn't get close to one number, so the limit doesn't exist. So those are our three cases when our limits do not exist. And we'll talk about how we deal with those, or how we figure those out as we move forward. All right, we good so far? Well, luckily there are some functions that the limits, it's really easy to find the limits. So I want to talk about some rules, some properties of limits, and then some nice functions where we can find the limits really easily. And that's all we're going to do for today, is talk about the graphical and table ideas, and then some nice functions. So properties of limits. So these are just operations that we can do with limits. The limit as x approaches c of some constant number b. B is never changing. So what's our limit going to be here? Our function is b, doesn't change. So what's our function getting close to? B. Stays b all the time. So limit as x approaches c of b is b. Just some constant. B is a constant. The limit as x approaches c of x, we can just plug in our number there, c. This is just a line that goes through the origin. As x gets close to 5, x is getting close to 5. That's all it's saying. B is a constant. So this is 2. Limit as x approaches c of 2 is just 2. Doesn't matter what x approaches. X could approach 1,000. The limit as x approaches 1,000 of 2 is just 2. Here the limit as x approaches 1,000 of x would be 1,000. Okay? The limit as x approaches c of x to the n, some power of n, is just our number to the power. So these are nice functions. A constant function is nice. A linear function is nice. A power of x is a nice function. I can just plug in c to get my limit. And then we can do the same thing for a root function. The nth root of x is another nice function. We can just plug in our value there. So I'm going to write over here, just to make a little note, these are nice functions. We like nice functions. So a linear function's nice. A power function's nice. A root function's nice. We can just plug in our values. A constant function's nice because our limit's just a constant. Operations with limits. We want to be able to do some arithmetic with limits. So we don't want just these simple functions. We want to combine simple functions into more complicated functions. And then we'll come up with kind of a family of nice functions that we can just plug in our value here. The limit as x approaches c of some constant times a function. I can just pull that constant out. So I can just multiply the limit by the constant. I can find the limit of the function and then just multiply by a constant. I can add and subtract limits. So if I'm adding and subtracting two functions, I can find the limit of that function by finding the limit of each of them and adding them together. And I should say plus or minus. So if I'm adding a bunch of functions together, I can just take the limit of each one individually and add those limits together. I can do the same thing with products and quotients. When I'm multiplying the two functions, I just multiply the limits. That's one downside of when math gets more complicated, there's more stuff to write. And the limit, we can do the same thing with a quotient as x approaches c. F of x over g of x. I can just take the limits of the quotients, or the quotients of the limits. And what do we have to be careful with here? What would our restriction be here? What has to be true about this thing in the denominator? The limit can be 0. So for this one, we say the limit as x approaches c of g of x not equal to 0. And then finally, we can take the power of a function, raise it to an exponent, and that is just the power of the limit. So this lets us combine functions in various ways and find the limits of these combinations. Well, if we combine these nice functions, a constant function, a linear function, powers of functions, roots of functions, what that lets us say is the limits of polynomials, which are just a bunch of these things added together, or rational functions, which are fractions made of polynomials. The limits of polynomials and rational functions we can find just by plugging in our x value. So we can combine these and say polynomials. and rational functions. Rational polynomials and rational functions are nice functions. We can just plug in the x value. Find the limit by plugging in the x value. And I'm going to just say substitution. And this is true as long as we don't run into some kind of problem like dividing by 0 or finding the square root of a negative number. Then we have to do some more work with our limits. And we'll talk about how we do that next time. So let's look at a couple of examples of finding limits of nice functions. So are we good with our operations here? All right. The limit x approaches 4 of the square root of x. Is a root function a nice function? That's one of our nice ones that we defined, right? I can just plug in x equals 4. So what is this limit? 2. The limit as x approaches 1 of x squared minus 2x plus 5. Polynomial, nice function. I can just plug in x equals 1. So what do I get for a limit here? Three, 4? Between 3 and 4? 4. And then finally, the limit as x approaches 0 of x plus 1 over x squared plus 5x minus 4. Do I get anything that we don't like happening when I plug in x equals 0? Do I end up with a 0 in the denominator? No. So I can just plug that number in. So when I plug in x equals 0, what do I get? 1/4. The limit of that function as x approaches 0 is 1/4. Negative, yes. Thank you. Because of this negative sign. All right, so polynomials, rational functions, as long as they don't give us some kind of problem, dividing by 0, square root of a negative number, if we have a root function, then we can plug in our x value to find our limits. We will talk about other kinds of functions, the kinds of functions where we used our graphs or our tables to find limits. So we'll talk about algebraic rules for finding limits next time. And the nice thing is our algebraic rules for finding limits are very much the same as our rules for finding vertical and horizontal asymptotes. All right, questions? Okay.